Hello everyone, this is another video on statistical mechanics. And in the previous class, we were discussing canonical ensemble. Okay, so I gave you a question about fermions. Two fermions here: G is equal to 1, G is equal to 2, and this one is epsilon, this one is 0. So um, here you have two fermions. You have to arrange those two fermions in these two levels, and for that you have to find the number of microstates and entropy. Alright. So how will you do it? See, two fermions are there, and for fermions, we know two fermions cannot be in the same state. Okay, if the spin is not mentioned, can't it be in the same state? So here, what will you do? Yeah, see, this is degeneracy is two here, right? That means I can do like this: 0, epsilon, epsilon. So I can like two levels here. So two fermions are there. So I'll arrange two fermions. For example, one fermion here, one fermion here. Fermions are indistinguishable. Then one here, one here, then one here, one here. Alright. So total energy for this one is epsilon, total energy for this one is epsilon, total energy for this one is 2 epsilon. Right. So this is our E1, E2, and E3. Okay. So what is the partition function for this? Z is equal to, summation Gi e to the power minus beta Ei, right? So this degeneracy is 2. So 2 into e to the power minus beta E plus 1 into e to the power minus 2 beta epsilon. This is epsilon. So 2 e to the power minus beta epsilon plus e to the power minus 2 beta epsilon. Okay, so this is the answer for partition function. Okay, how to calculate the internal energy? Minus del by del beta of ln z, right? So minus del by del beta of ln 2 e to the power minus beta epsilon plus e to the power 2 beta epsilon. So you take the derivative for it. Minus is there outside. 2 e to the power minus beta epsilon plus e to the power minus 2 beta epsilon. Then the derivative of this one is minus 2 epsilon e to the power minus beta epsilon minus 2 epsilon e to the minus 2 beta epsilon. So minus 2 beta 2 epsilon, you can take it out. That will be 2 epsilon e to the minus beta epsilon plus sorry plus e to the power minus 2 beta epsilon divided by 2 e to the power beta epsilon plus e to the power minus 2 beta epsilon. So this will be your what? This will be your average energy, alright? Now what is the Helmholtz free energy? A is equal to minus kT ln z, right? So you can just put it there, minus kT ln z is how much? E to the power 2 e to the power minus beta epsilon plus e to the power minus 2 beta epsilon is your z. Okay, this is a Helmholtz free energy. Okay. So these were some of the examples in which spin was not mentioned. Suppose spin is mentioned if spin is mentioned directly or indirectly. Okay, spin is mentioned directly or indirectly. How will you solve it? Say, for example, let's have 4 electrons and two energy levels. Two energy levels, 0 and epsilon, and first excited state. First excited state is doubly degenerate. Is doubly degenerate. So okay, we have to find what partition function again. All right. So we have four electrons, and you have two energy levels, 0 and epsilon. 0 epsilon, four electrons are there. Electrons are what? First tell me. Bosons or fermions. Electrons are fermions. Okay. And electrons have spin half. So it's indirectly given. The spin is indirectly given in this question. And yeah. So four electrons. Okay. Four electrons are there. Spin is half. So here, see, number of electrons is 4, and number of energy levels is 2. Okay. So how do you find it? I'll find it. Okay, see. First of all, a spin is half. Spin is half. That means multiplicity. That means one multiplicity will be 2s plus 1. That is 2 into half plus 1. So that is 2. So maximum 2 electrons can be in one state. Alright, that is thing. Maximum 2 electrons can be in one state. That is okay. So 4 electrons are arranged this way. Right? 4 electrons then arranged this way. Right. Okay, wait just a second. Okay. Oh, okay. First excited state is doubly degenerate. Alright, alright. Okay, I made a mistake. No, not this way. Wait. First excited state is doubly degenerate. That means this is 0. This is equal to 2 epsilon. That means I can also do this as doubly degenerate means I can do it twice. 0 epsilon epsilon. Now okay, each level will split further in 2s plus 1 levels. Okay, this is the rule. So 2s plus 1 is how much? 2 into half plus 1, that is you have 2. So each level will be split into 2. So I can do this as like this 0. Okay, got it? Yeah, is it alright? Hmm. So now how many levels we have? How many levels we have? 6 levels. 1, 2, 3, 4, 5, 6. 6 levels. That means Ni is equal to 6. How many electrons we have to? Sorry. Gi is equal to 6. How many electrons we have to take into consideration? 4. So Ni is equal to 4. So for fermions, number of arrangements is what? For fermions, number of arrangements. Number of arrangements is how much? Gi C Ni. So Gi is your 6, C Ni is your 4. So 6 factorial divided by 6 minus 4 factorial into 4 factorial, that is 6 factorial divided by 2 factorial into 4 factorial. If you cancel this, this will be 6 into 5. This is 30, so 15. So 15 ways are there to what? Arrange this is this system, right? There are 15 ways to arrange this. Okay, how will we solve now? Do it. See, um, see, there are 15 levels. So for to find the partition function, it won't be asked in the exam, but just for your clarity, to find partition function, we have to draw those 15 levels, isn't it? We have to draw those 15 levels. There are, you see, 6 levels. Okay, this is for 0. This is for epsilon, isn't it? So there are 4 electrons. Okay, and each electron will be there in different levels. They cannot be in the same state. So electron here. We'll do accordingly. So this is your 2 epsilon. Now I'll just leave a space here. This is also 2 epsilon if you see. Now I'll go on one more step. This is also 2 epsilon if you see, isn't it? Because both are here 0, and if any other step is left here. Okay, this is for 2 epsilon, isn't it? Any more 2 epsilons are there if you can, yeah, so it's there. I can have the particle, these two here, and these two here, right? Yeah, so this one, and this is also 2 epsilon. I can have the particle here and here also, and then there's one. Okay, one more is there. That is this and this. Okay, two zeros, yeah, and these two. Okay, so this is also your 2 epsilon. So there are 6 values of 2 epsilon. That means 2 epsilon has degeneracy as 6. Degeneracy is 6. Okay, this is your energy 1, and degeneracy is 6. We found out. There are no more arrangements you can do in the energy 2 epsilon. Uh, then let's try more. Suppose this is a 0, this is 0 epsilon. For example, we'll only keep one particle in the 0. So 3 particles in epsilon, 1, 2, 3. So this is a 3 epsilon. This is one particle here. 1, 2, 3. This is also 3 epsilon. Uh, one particle here. And this is a 3 epsilon, right? Yeah. This is also 3 epsilon. What any other way we can arrange them? Any other way we can arrange them? We can leave this one if we can. This is one particle here, and yeah, this is also a possibility for 3 epsilon. This is 0 epsilon. Okay. Any more 3 epsilons we can do? We can do the exact same thing, keeping this particle over here. Okay, exact same thing here, and all those arrangements that we just did. 0, 0 epsilon here, 3 epsilon, 3 epsilon here. Exact same way, means more 4 values, 4 here, right? 0 for 0 here, and for epsilon, what can be the state here? This is also, so how many 3 epsilons are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 3 epsilons are there. So energy level, second energy level is 3 epsilon, and your degeneracy is how much? Degeneracy is 8. There are 8 levels which have the same energy value as 3 epsilon. Alright. Now let's try to arrange. Let's not have any particle in the 0 level. We have taken all, at least one particle in the 0 level so far. So if we do not keep any particle in the 0 level, so that means all the particles should be here in the epsilon level, and that's it. This is only one arrangement here, 4 epsilon, because we cannot interchange them because these are indistinguishable, and we will never be able to recognize which particle is which. So we won't be able to exchange their positions. So only one arrangement is there in epsilon. So E3 is equal to 4 epsilon, and G3 is equal to 1. Okay, so we have 3 energy levels. This is first one is 2 epsilon, whose degeneracy is 6. Second stage is your 3 epsilon, whose degeneracy is 8, and third one is the 4 epsilon, whose degeneracy is 1. So if we calculate the partition function, z is equal to epsilon I, sorry, summation I g I e to the minus beta e n. So let's do it. Okay, let me write it first. EI, EI. This is GI. EI is a 2 epsilon. For 2 epsilon, DGS is how much? DGS is 6. DGS is 6. For 3 epsilon, DGS was 8. For 4 epsilon, there was only one energy level which could have, one state which could have achieved it. So if we write the e-to-the minus 2 beta epsilon plus 8 e-to-the minus 3 beta epsilon plus 1 e-to-the minus 4 beta epsilon. So this is a z. Is it alright? Yeah. So finally we go to partition function. So this is a very conceptual question again, and you need to really understand the concept if you want to solve it. One more question. One more question. The more questions we do, it's better for us. Let, let you have, suppose you have 3 spin half particles and 2 energy levels. 2 energy levels minus epsilon and epsilon. Alright. So we have to find partition function again. We have 3 spin-off particles and 2 energy levels minus epsilon and epsilon. Find the partition function. Okay, you have 3 spin-off particles and 2 energy levels minus epsilon epsilon. 3 spin-off particles. Is it alright? So again spin half. That means each energy level will split into how many levels? 2 into half plus 1. That is 2. So each energy level will split into 2 energy levels. Epsilon epsilon minus epsilon minus epsilon. Alright. Okay. So you have 3 spin-off particles. So Ni is your 3. And there are how many levels here? Gn, right? Ga is equal to 4. Is that alright? Is it alright? So what is the number of ways in fermions? This is a fermion spin-off particle. So number of ways of distributing is Gi, Cni, right? So 4C3. That is a 4 actually. 4C3 is actually 4. Um, yeah. So 4 ways of arranging these particles. Let's do. See, I'm doing in pairs. Minus epsilon minus, so that you won't get confused. Okay, so three particles are there, right? So one, two, three. These are indistinguishable. Four means are indistinguishable. Total energy is minus epsilon. Okay. One here, right? Minus epsilon. How I'm writing this? I'm just adding a minus 2 epsilon plus epsilon, that is minus epsilon. Minus 2 epsilon plus epsilon, that is minus epsilon. One particle here and two particles here. That will give me 2 epsilon minus epsilon, that is epsilon. Again, one particle here and these two here. So this is epsilon. So four energy levels I got. Okay, so degeneracy. So first energy level is minus epsilon. With degeneracy is 2. Is 2. It's twice repeated twice. E2 is epsilon and G2 is E2. So it's also repeated twice. So again, partition function is very easy. Partition function. Partition function will be z is equal to summation gi into the minus beta en, which is um, what 2 e to the power minus beta epsilon minus beta minus epsilon plus 2 e to the power minus beta epsilon, that is 2 e to the power beta epsilon plus 2 e to the minus beta epsilon. If you actually take the 2 common, e to the power beta epsilon plus e to the power minus beta epsilon, and if you divide it by 2 and multiply it by 2, this is actually your cos hyperbolic beta epsilon. Okay, so this is your partition function. Is it alright? Next question, question number 3. You have two photons, okay, and two energy levels, epsilon and 2 epsilon. Right? Find the number of ways, number of ways of distribution. Right? Okay. You have two photons, two energy levels, epsilon and 2 epsilon. So photons, right? So photons are what? Photons are bosons. So photons are bosons. That means spin is 1. Spin of photons is 1. So two energy levels, epsilon and 2 epsilon. So each energy level will split into 2s plus 1 values. 2s plus 1 is how much? 2 into 1 plus 1. That is 3, right? So yeah, just 1, 2, 3, 1, 2, 3. So this is your epsilon. This is your 2 epsilon. Is it equals to alright? So what is the G here? 2 photons. That means Ni is 2. This is 6 energy levels. So Gi is 6. Okay. So your number of ways of distribution for bosons is what? Ni is Gi minus 1 whole factorial divided by Ni factorial into Gi minus 1 factorial. Okay. So 2 plus 6 minus 1 factorial divided by 2 factorial, 6 minus 1 factorial. Okay. So if you see this is a 7 factorial divided by 2 factorial into 5 factorial. This is 7 into 6. 7 into 6 by 2, that is 21. So there are 21 number of ways to arrange this system. Okay. Next question, question number 4. So you have two spin zero particles. Okay, two spin zero particles and two energy levels. I think you'll be able to solve this now. And degeneracy of ground state. Okay, G of JEST and degeneracy of ground state is 2 and degeneracy of first excited state is 2. So partition function you have to find out. You have to find the partition function. Try this question. We have done enough now for you to be able to solve these type of questions. I hope you got the answer. So two particles, spin is 0, two energy levels, epsilon to epsilon. Alright. Hmm? So each energy level will split into how many? See, first of all, their degeneracy is 2. So first of all, I will do the original diagram. That is, this is the original one. Like their degeneracy is 2, na? So like this, original. Then I will do the splitter. Okay. First, because in the previous cases, what exactly happened? I directly splitted them. Why? Because their degeneracy is 1. There is no clarification on degeneracy, so we will consider them as 1. That's why I just directly splitted them. In the previous case also, the splitting happened directly, two levels, because their degeneracy was not given. That means it is 1. But here what happened? Here their degeneracy is already given. So first of all, we have to do the degeneracy. That is 2 epsilon to epsilon. For this is epsilon epsilon. Now we will do splitting. Okay, so splitting will be spin is equal to 0, 2 into 0 plus 1. That is uh, that is 1. So only one splitting. That means this will be exactly like this. Okay, so four levels. Okay, so see, if you don't write the degeneracy, what problem will you have? You will first write it as epsilon to epsilon, then you will do the 2s plus 1 is equal to 1. So you will do the splitting only two levels, so that will be wrong, right? So this is the way. So degeneracy is now total degeneracy is 4. Total particles are 2. So number of ways is GNCNI 4C2. That is 4 factorial divided by 2 factorial and 2 factorial. It's 4 into 3. So this is 6. Okay, so 6 ways we can now distribute. So let's distribute them. Okay, my bad. Sorry. This is for fermions. Sorry. These are bosons. Spin is 0. That means bosons. Ni is 2. Gi is 4. The number of ways is Ni plus Gi minus 1. Ni factorial. Gi minus 1 factorial. 6.5 factorial divided by this is 10. It's 10 number of ways we can arrange them. Alright. So we are asked partition functions. We have to arrange them. 2, 3, 4. 4 ways were there. So epsilon, 2 epsilon, 2 epsilon. So how many photons are there? Sorry, how many particles? 2 particles. So 1, 2, 2 epsilon energy. 1, 2, 3 epsilon. 1, 2, 3 epsilon. Try to do yourself first. 1, 2, 3 epsilon. 1, 2, 3 epsilon. Now then, 1, 2, 4 epsilon. Did I miss anything? 1, 2, 3, 4, 5, 6, 6 levels. We should have 10, right? Okay, yes. These are spin 0. So these are bosons. No? So bosons don't have restrictions. They can be together. Okay. This is 2 epsilon. My bad. Here. This is 2 epsilon. Here this is 4 epsilon because this energy was 2 epsilon. This is also 4 epsilon. This is 1, 2, 3. How many levels now? 1, 2, 3, 4, 5, 7, 8, 9, 10. Yes. How many 2 epsilons are there? 1, 2, 3, 3. So if I draw the table, EI, GI. So 2 epsilon is repeated 3 times. 3 epsilon is 1, 2, 3, 4. 4. 3 epsilon is repeated 4 times, and 4 epsilon is remaining 3 times. So if I write the partition function, that will be summation I gi e to the power minus beta ei. So 3 e to the power minus 2 beta epsilon plus 4 into e to the power minus 3 beta epsilon plus 3 into e to the power minus 4 minutes. Okay, this will be your partition function. Is it clear? Okay, next give a heading for approach for classical particles. Okay, write a question. Question number, I think it will be question number 5. Four classical particles and three energy levels. Minus epsilon, 0 epsilon. Four classical and distinguishable particles. Some and respective degeneracy. Or G1 is equal to 2, G2 is equal to 1, G3 is equal to 2. Find partition function. Okay. Four classical and distinguishable particles and three energy levels. Epsilon minus 0 minus epsilon respective degeneracy of G1 2, G2 1, G3 is 2. Find the partition function. Okay, how to solve this? Three energy levels. Okay, it's a very straightforward question. There's nothing else here. Two, one, two. So partition function we will write directly here. It's 2 e to the power minus beta epsilon minus minus plus plus e to the power 0 plus 2 e to the power minus beta epsilon. So 2 more than 2 e to the power beta epsilon plus e to the power minus beta epsilon. For n particles, for example, this is distinguishable. Okay, so Zn will be Z1 to the power n. If it is indistinguishable, Zn will be Z1 to the power n divided by n factorial. Okay. Yeah. So this was your approach for fermions and bosons and how to arrange them. Okay. In the next session, we will be discussing about uh, harmonic oscillators. Okay. Harmonic Oscillators. Harmonic oscillators are two types. Classical harmonic oscillator and quantum harmonic oscillator. Quantum harmonic oscillator. Classical harmonic oscillator and quantum harmonic oscillator. Okay, quantum mechanical harmonic oscillator, whatever. Is it all right? Yeah. Okay. Anyway, let's start this quantum harmonic oscillator. Quantum mechanical harmonic oscillator. Okay, quantum mechanical harmonic oscillator. So write down if we have a system of n identical independent independent non-interacting distinguishable particles. Non-interacting means what? Potential energy is zero. Okay. Distinguishable distinguishably placed quantum harmonic oscillators in one dimension. Okay, in one dimension. So, okay, first of all, we'll see one by one what is the meaning of everything. First of all, identical. What is the meaning of identical? Identical means similar in physical properties. Okay. Then comes next word is your independent. What do you mean by independent? Motion of one is not motion of one is not affected. Not affected by harmonic oscillator. It's not affected by harmonic oscillator. Next is the non-interacting. What do you mean by non-interacting? Non-interacting. Non-interacting. What do you mean by non-interacting? No interaction with each other. That means your potential energy is zero. Potential energy is zero. Alright. Now last is your distinguishable particles. Distinguishably placed. Distinguishably placed. That means localized. Okay. Okay. So these are some of the terms that you need to be acquainted with. Alright. For quantum harmonic oscillators, we know energy eigenvalue is equals half h cut omega. Alright, where the n is starting from 0, 1, 2, 3, 4. Okay. Okay. So for how will we calculate the partition function in these cases? How will we calculate the partition function? Our main aim has always been to calculate partition function in statistical mechanics. Okay? Z is equal to summation I g I e to the power minus beta e m e. Okay, and see En is what? M plus half h cut omega all right. So E0 is your h cut omega by 2. So energy values are what? H cut omega by 2, 3 h cut omega by 2, 5 h cut omega by 2, 7 h cut omega by 2, isn't it? So these are the energy values. Hmm. And these are what non-degenerate. These are non-degenerate for 1D case because this is a 1D harmonic oscillator. So for 1D, this is not non-degenerate means there is no degeneracy. That means the energy is repeated only once. Energy is not even repeated. Is not repeated. That means only one energy value. That means half h squared omega is only there once. There is no other value of n for which the energy will be half h squared omega. Alright. For example, there is this 2D harmonic oscillator. Suppose the value for it is nx plus ny plus 1 h squared omega. So here, if I say h squared omega is the energy value, so is it non-degenerate? No, because for nx is equal to 0. Okay, okay, no, 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 not. For example, this is 2. Nx is 0, ny is 1. Then e is equal to what? 0 plus 1 plus 1. H squared omega, that is 2 h squared omega. But if I say again that nx is 1 but ny is 0, then your energy value will be 1 plus 0 plus 1 h squared omega, that is your 2 h squared omega. So this is not non-degenerate, this is degenerate. Degenerate means it has some degeneracy. That means the energy is repeated twice or thrice or whatever times there is. So, but this is 1D harmonic oscillator, and 1D harmonic oscillator, the energy is non-degenerate. Okay? Energy is not repeated. So these are the non-degenerate values. That means degeneracy is 1 for everything. So G is 1. So if I calculate the Parsons functions, it will be e to the power minus beta h squared omega by 2 plus, just put the values. Don't no need to do the degeneracy term. 3 beta h squared omega by 2 plus e to the power minus 5 beta h squared omega by 2 plus, it will go on and on. Okay. Yeah. So if I take it common, if I take e to the power minus beta h squared omega by 2 common, so 1 plus e to the power minus beta h squared omega, you do it yourself. Okay, try to do it, don't just copy it, plus e to the power minus 3 beta h squared omega, it will go on and on like this again. Okay, so if you see, this is actually what this is actually, the inside part is actually the it's an expression for 1 by 1 minus e to the power. Okay, this is actually the binomial expansion for e to the power minus beta h squared omega to the power minus 1. Okay. Hmm. It's because 1 minus x, like, okay, so I can write it as e to the power minus beta h squared omega by 2, 1 by 1 minus e to the power minus beta h squared omega. Okay, you can do this way. Otherwise, you can say this is an GP. This is in GP, geometric progression. That is e to the minus beta h squared omega is the r. Like GP is what, a by 1 minus r. So a is the initial value, that is 1, and minus r. R is the one that is divided. Keep it that is divided continuously. So if you divide e to the power minus beta h squared omega, it will go on and on like this. Okay, so this is it, and yeah. So this is the partition function for it. Okay, I can extend it a bit. Just a second. Okay. So what did I get in the previous slide? I got it as z is equal to e to the power minus beta h squared omega by 2, 1 minus 1, 1 by 1 minus e to the minus beta h squared omega. Is that all right? Now I can write it as, can I this is minus, so can I do like this, beta h squared omega by 2, 1 minus e to the power minus beta h squared omega, right? Now I will just multiply it inside, e to the power beta h squared omega by 2 minus e to the power minus beta h squared omega by 2, isn't it? Isn't it? Yeah. So if you see e to the power x minus e to the power minus x by 2, that is actually sine hyperbolic x. Okay, so I will divide it to multiply it to, okay, so this thing will become sine hyperbolic x. That means 1 by 2 sine hyperbolic, what is x? H squared omega by 2 here. Okay, so don't get confused. Sorry, beta is there also. Sorry, beta h squared omega by 2. Yeah. So this is, I can write it as also sine 2 sine hyperbolic beta h squared omega by 2 whole inverse, isn't it? Because it's in the denominator. So this is your partition function for 1D harmonic oscillator, 1D quantum harmonic oscillator. Okay, partition function for 1D quantum harmonic oscillator. For n particles, it will be for n particles it will be what? Zn is equal to z1 to the power n. That means 2 sine hyperbolic beta h squared omega by 2 inverse n to the power n. Okay, so I can write it as 2 sine hyperbolic beta h squared omega by 2 to the power. So this is the whole inverse. Okay, so whole to the power minus n, isn't it? Yeah. So this is your partition function. From here we can calculate what? Internal energy or average energy. Average energy will be minus del by del beta of ln z. So let's put it minus del by del beta of ln z. Z is what we just calculated 2 sine h hyperbolic beta h squared omega by 2 to the power minus n. Okay, so it's ln. So minus n will go out, minus n plus n del by del beta of ln 2 sine hyperbolic beta h squared omega by 2. Is that all right? Now I can take the derivative of this. This will be 2 sine hyperbolic beta h squared omega by 2, and derivative of inside part, that is 2 cos hyperbolic bit into h squared omega by 2. Is it all right? So 2 2 will be cancelled. So this cos by sine, that will be your cot, right? So nh squared omega by 2 cot hyperbolic beta h squared omega by 2. Is that all right? Okay. So this is your average energy. What is the Helmholtz free energy? You try to calculate this. This is very easy. Helmholtz so is easy, no? A is equal to minus kT ln z. So minus kT ln 2 sine hyperbolic beta h squared omega by 2 to the power minus n. So minus n will nkt ln 2 sine hyperbolic beta h squared omega by 2, isn't it? Nothing in it. Okay, so this way you can calculate a lot of things. Entropy you can calculate. Entropy is what? Entropy is minus del A by del T at volume and n are constant. You can calculate that. Pressure is what? Minus del A by del V. Okay, at n and t are constant. Chemical potential mu is. You please try to calculate this on your own. Okay, TV. Is that all right? Yeah, please. Gives free energy is what? Gives free energy. G is equal to mu n. Okay. So this is a what? Quantum harmonic oscillator. Is that all right? Is it all right? Quantum harmonic oscillator. Okay. Okay, I will give you a question for homework. Homework. Okay. Question number 8 will be, I think, 7, I think. Okay, you have n spin half particles placed in a magnetic field B, okay, and pointing along z direction, pointing along z direction. Then what is the probability? Then what is the probability that r particle will be in spin up state? Okay. Question number 8. Okay, I would like you to read this book, R.K. Patharia. Okay, this book is very good, and try to solve its exercise. First exercise 1.1 to exercise 1.10. Try to solve these 10 questions from the first exercise, from the first chapter. Okay, if you're not able to solve, we'll try to. So yeah, these are very these are tough questions, very conceptual, and you try to solve. Otherwise, I will solve someday after our like syllabus is over. We'll try to solve one by one. Okay. Okay. So yeah, thank you very much for watching. And if you want another question, just wait. Write another question. And number 9. Consider a system of n distinguishable particles. N distinguishable particles with two energy levels for each particle. A ground state with energy 0, with energy 0, and an excited state with energy epsilon greater than 0. What is the average? It's the average energy per particle as the system temperature T tends to infinity. Options are 0, 7/2, 7, infinity. Yeah. So this is the question. Try to solve it, and we'll be solving more questions in the next session. Okay. Thank you very much.